Hello everyone. We begin now with the next chapter, eigenvalues and eigenvectors. I already explained to you in the previous capsule how these problems arise. We took one example from geometry and one example from physics, and in both cases we came with the following equation of finding a vector v, non-zero vector v, such that av equal to lambda v, where lambda is a scalar. So let us formally start this new, develop this new concept on eigenvalues and eigenvectors. Given an n cross n matrix A, it's a square matrix, a non-zero vector, non-zero has been underlined, a non-zero vector v is said to be an eigenvector of A if there exists a scalar lambda such that AV equal to lambda v. And lambda is called the eigenvalue associated to the eigenvector v. Geometrically, we can think of A as a linear transformation taking Rn to Rn. And then what does this linear transformation do to the eigenvector? It gives you simply a multiple of the multiple of the vector lambda v. And in other words, the matrix A acts as a collineation. It collineates V and gives you a collinear vector lambda V. That is, V and lambda V are proportional. So now, if it takes A, if A takes V to lambda V, then what happens when I multiply this equation by 2? A of 2V equal to lambda times 2V. A of 3V is lambda times 3V. More generally, if for any scalar C not equal to 0, C has to be non-zero because eigenvectors are supposed to be non-zero. So A of CV is lambda times CV. So CV is also an eigenvector. So these eigenvectors are really considered to be one and the same, because if you know one, then you know others simply by multiplying by C. So you have a line of, you got a whole line of eigenvectors. And so this all these CVs, all these vectors CV have the property that A takes them as input, and the output is simply multiplication by lambda, a collineation by a factor of lambda, or stretches by a factor of lambda. The stretching factor is called the eigenvalue. So now let us keep this in mind and let us understand geometrically this matrix, the eigenvalues and eigenvectors of this matrix A: cos pi by 3 minus sin pi by 3 sin pi by 3 cos pi by 3. Explain why there is no eigenvector in R2. Well, geometrically, what is A? A is a rotation through angle pi by 3. That is, it is a rotation of the plane by angle pi by 3. And no non-zero vector can be an eigenvector, because if you take a non-zero vector, that vector gets rotated by angle pi by 3. So how can AV? AV is simply rotating V by angle pi by 3. So obviously V and AV cannot be collinear. So therefore directly we see through geometrical considerations that this matrix A has no eigenvector. On the other hand, let us take a matrix which has a nullity. Suppose a non-zero vector lies in the null space of the matrix. What does it mean to say that V is the null space? AV equal to 0. But 0 is 0 times V. So AV equal to 0 times V. And V is non-zero. I'm assuming that there is a non-zero vector in the null space. That is, the nullity is positive. That means V is an eigenvector with eigenvalue 0. Remember, eigenvalue can be 0. Eigenvector is non-zero. So V is an eigenvector with eigenvalue 0. Obviously, this is obviously the converse is also true. In general, 0 is an eigenvalue of A if and only if the nullity of A is positive, or equivalently, the rank of A is strictly less than n. So this is another example of an eigenvector. Third example, I take a matrix A to be 1 minus 1 minus 1 1. Obviously, the rank is 1 and the nullity is 1. And so by the previous example, 0 must be an eigenvalue. In fact, multiply the matrix by 1 1. So A applied to 1 1 is 0 0. So 1 1 is the null space. So eigenvector is 1 1 with eigenvalue 0. Now on the other hand, suppose I multiply A to 1 minus 1. Let us calculate A of 1 minus 1. So if you do the matrix multiplication, you get 2 minus 2, which is 2 times 1 minus 1. So again, 1, 1 is an eigenvector and the eigenvalue is 2. Eigenvalue is 2. So we got two eigenvalues 0 and 2. Are there any others? Well, an n cross n matrix cannot have more than n eigenvalues. A 2 cross 2 matrix cannot have more than 2 eigenvalues. I already produced 2 and that's all. We will prove this theorem later that a matrix, what are the eigenvalues of a n cross n matrix, how to find them. The third example, let us take, is a skew symmetric 3 by 3 matrix. A 3 by 3 skew symmetric matrix has determinant 0. I hope you're done this exercise now. What about 2 by 2 skew symmetric matrix? Already here is one 0 a1 minus a1 0. This 2 by 2 submatrix that is skew symmetric. What is the determinant? a1 squared may not be 0. So for 2 by 2 skew symmetric matrices, determinant may not be 0, but for 3 by 3 skew symmetric matrix, determinant is compulsorily 0. So the nullity is positive and we know 0 is an eigenvalue, and find the corresponding eigenvector. Find the corresponding eigenvector and try some things out. Take some combinations of so suppose I take a3 minus a2 a1 or some such thing and see whether you get 0. So you will get you will try to find an eigenvector. You will try to find an eigenvector for this. So you could try a3 minus a2 a1, for instance. Suppose that a3 minus a2 a1. See whether that works. If that doesn't work, try to modify it appropriately. So you get an eigenvector, and I'm assuming that a1 squared plus a2 squared plus a3 squared is non-zero, just to make the problem interesting. And so that is an exercise for you. So now, after these three examples, let us come to a systematic way of finding eigenvalues and eigenvectors for a matrix. So to begin with, we shall work with real matrices, but eventually we'll have to work with complex matrices, and we'll have to allow the eigenvectors to be complex numbers. We'll have to allow the eigenvalues to be complex numbers and eigenvectors to be vectors in Cn. But right now, as far as to the extent possible, the examples will be from real matrices. So take an n cross n matrix A, and suppose V is an eigenvector with eigenvalue lambda. That means what? AV equal to lambda V, and V is non-zero. If V is non-zero, I can write this equation as A minus lambda IV equal to 0. V is non-zero. That means that there is a non-zero vector in the kernel or the null space of A minus lambda I. That means the nullity of A minus lambda I is positive. That means that the rank is strictly less than n. That means the determinant is 0. So this lambda must satisfy the condition determinant of A minus lambda I is 0. Conversely, suppose if determinant of A minus lambda I is 0, then the nullity of A minus lambda I is positive. That means there's a non-zero vector V such that A minus lambda IV is 0. That means that AV equal to lambda V and V not equal to 0, and lambda is an eigenvalue corresponding to the eigenvector V. So we have seen it in both ways. So lambda is an eigenvalue of A if and only if determinant of A minus lambda I is 0. So that, let us summarize these observations in the form of a theorem. The eigenvalues of a matrix are precisely the roots of the polynomial determinant of A minus xi equal to 0. Now you may write determinant of A minus xi, or you may write determinant of xi minus A, doesn't matter because the right hand side is 0. Sometimes, in fact, often we are going to write determinant of xi minus A. This polynomial is called the characteristic polynomial. Determinant of xi minus A is going to be called the characteristic polynomial, and this equation is called the characteristic equation of the matrix. Note that the characteristic equation is a polynomial equation. What is the degree of this polynomial equation? It's an nth degree polynomial equation. You should write this out for the 3 by 3 case and convince yourself for a 3 by 3 matrix, it's a cubic polynomial, and for a 4 by 4 matrix, it's a 4th degree polynomial. And you will be convinced that for an n cross n matrix, this is a nth degree polynomial in one variable x. So it's a polynomial equation. It's a very nice, innocent looking thing. This polynomial equation may or may not have real roots. As you know, you can take a quadratic equation. The quadratic equation, the coefficients may be real, Nevertheless, the roots could be complex. Of course, if the coefficients are real and if the roots are complex, then these complex roots must appear in conjugate pairs. But the complex roots will appear in conjugate pairs under the hypothesis that the coefficients are real. Of course, if the coefficients are complex, then, well, x minus I equal to 0. That's a first degree polynomial equation with complex coefficients. Of course, it has root I, it doesn't have root minus I. So some of these basic things from equations you should recall. That is, if the equation has real coefficients, complex roots appear in conjugate pairs. It's a useful thing to know. And sometimes you also know that the roots may get repeated. For example, if you are encountered quadratic equations with repeated roots, it could be x minus 1 the whole squared is 0. Roots are 1 comma 1. You must repeat the root as many times as it appears in the equation. So on the other hand, if your polynomial factorizes as x minus 1 cube into x plus 2 squared, then what are the roots? 1 comma 1 comma 1, and then minus 2 comma minus 2. Minus 2 is a double root and 1 is a triple root. So roots may be repeated, and you should repeat them as many times as the factor appears in the factorization. Let us now go back to the previous example: cos theta minus sin theta cos theta. Instead of freezing the value of theta to be pi by 3, let us work with theta. Let us calculate the eigenvalues by first finding the characteristic polynomial. What is the characteristic polynomial? Determinant of xi minus a equal to 0. Xi minus a. What is that going to be? X minus cos theta sin theta minus sin theta x minus cos theta. 2 by 2 matrix. What's the determinant? X minus cos theta squared plus sin squared theta. What is that? X squared plus 1 minus 2x cos theta equal to 0. That is the characteristic equation. Check that it has got two complex roots. There are no real roots. So in the very first example, we approached it geometrically first. Now we are doing the same problem again, but algebraically. Let us see the second example: 1 minus 1 minus 1 1. What is the characteristic equation? Determinant of xi minus a equal to 0. Xi minus a. What is that? X minus 1 1 1 x minus 1. So what is the determinant? X minus 1 the whole squared minus 1. What is it? X squared minus 2x. X into x minus 2. Roots are 0 and 2. Let us see the third example now. Compute the eigenvalues of 1 2 minus 1 2 2 0 1 2 minus 1. Already you see that the first row and the third row are equal. So 0 must be an eigenvalue, right? Let us calculate using the characteristic equation, determinant of a minus lambda I, or you can take determinant of lambda I minus a. Doesn't really matter because we're going to equate it to 0. So 1 minus lambda, 2 minus 1, 2 2 minus lambda 0, 1 2 minus 1 minus lambda. Expand using the first row. 1 minus lambda times 2 minus lambda 0 2 1 minus lambda minus 1 minus lambda, excuse me, minus 2 times 2 1 0 minus 1 minus lambda. Third one minus 1 into this 2 by 2 subdeterminant. Expand this whole thing, you get this factorization: minus lambda into lambda squared minus 2 lambda minus 4. One root is 0, and the other root, you have to solve this quadratic equation: 1 plus minus root 5. Okay, let us take one of the eigenvalues, 1 plus root 5, and try to find the eigenvector. So eigenvalue lambda is 1 plus root 5. What is the eigenvector? We have to solve, we have to find a non-zero v such that AV equal to lambda v, or A minus lambda IV equal to 0. Here is the equation: A minus solve A minus lambda. Lambda is what? 1 plus root 5 I applied to v. V is what? X1, x2, x3 equal to 0. We want a non-trivial solution. We want a non-trivial solution because an eigenvector is supposed to be a non-zero vector. So let us compute a minus 1 plus root 5 I. It is minus root 5, 2 minus 1, 2, 1 minus root 5 0, 1, 2 minus 2 minus root 5 applied to x1, x2, x3 is 0. Let us perform row operations. I want to first get rid of this minus root 5. How do I get rid of this? R1 prime equal to R1 plus root 5 R3. I want to get rid of this 2. R2 prime equal to R2 minus 2 R3. When I perform those operations, what do I get? I get 0, 2 plus 2 root 5, minus 2 root 5 minus 6, 0, minus 3 minus root 5, 4 plus 2 root 5, 1, 2, minus 2 minus root 5. Of course, I'm going to simplify it further. I'm going to get rid of this factor of 2, unnecessary factor. So R1 prime equal to 1 half R1. That will simplify it even further. 0, 1 plus root 5 minus 1 minus root 5 minus 3, 0 minus root 3 minus, excuse me, 0, 1 plus root 5 minus root 5 minus 3, 0 minus root 3 minus root 5, sorry, 0 minus 3 minus root 5, 4 plus 2 root 5, 1, 2 minus 2 minus root 5. Now, the first two rows are proportional. Why are the first two rows proportional? Take the 2 by 2 determinant, this 2 by 2 subdeterminant. What is the determinant? Do the calculation. 1 plus root 5 multiplied by 4 plus 2 root 5 and subtract 3 plus root 5 the whole square. You get 0. So that means that these two rows are proportional. Once these two rows are proportional, I can forget about the second row and I can just work with the first row and the third row. The first row will give you 1 plus root 5 x2 minus 3 plus root 5 x3 equal to 0. And the last equation gives you x1 plus 2x2 minus 2 plus root 5 x3 is 0. There is a pivot in the first column. And so x1 cannot be a free variable. X1 has to be expressed in terms of the free variables. Now you can take, of course, if you do further row operations, you will realize that the free variable will be x3. There can be, we can produce a pivot in the second column as well. So the non-pivotal column is the third column, and then you can take x3 as a free variable, and you can find x2 in terms of x3. So I can give some value of x3 and you can get one solution. Other solutions are multiples. Remember, right hand side there is 0. So if you find one solution, then all solutions can be obtained by simply multiplication by scalars. So I'll just first find one solution, and that should be enough because all solutions are obtainable simply by scaling. So here look at this equation: 1 plus root 5 x2 minus root 5 plus 3 x3 equal to 0. So I can take x3 to be 1 plus root 5, x2 to be 3 plus root 5. Already got your x2 and x3, and that gives you x1 root 5 plus 1. So you got your eigenvector, root 5 plus 1, root 5 plus 3, root 5 plus 1. Check, multiply AV, do the multiplication, calculate AV, and you check that AV will be equal to the eigenvalue times 1 plus root 5 times V. You can do the check if you like as a spot check. So that's an eigenvector with eigenvalue 1 plus root 5. So this example should convince you that if you have done the calculation correctly, if your eigenvalue calculation is correct, if you got your lambda correctly, and if you write A minus lambda I V equal to 0, and if you perform row operations, you must get one row must at least become 0. If you have done the calculation wrongly, if your eigenvalue calculation is wrong, then you will get that this you're very likely to get that you will conclude something like, oh, 0 is the only solution. Remember, eigenvector is non-zero. So if you do this calculation and you realize that, hey, x1, x2, x3 is forcibly 0, 0, 0, then that should give you immediately, that should send the warning signals that maybe your eigenvalue is wrong. Maybe you should go back and correct it. So just these are some internal checks and balances that I'm trying to draw your attention to. It will be useful for you to. So now we have seen several examples. We have introduced this new concept of eigenvalues and eigenvectors. We have seen many examples already now, 4 in fact. One of them is a 3 by 3 case that we have worked in detail. Now it's time for a formal theorem. The first theorem If A is an n cross n matrix and lambda 1, lambda 2, lambda k be distinct eigenvalues of A, this k is not the same as n, by the way. This k could be less than n. We could be looking at a 10 cross 10 matrix A, and we could be looking at 4 distinct eigenvalues. And v1, v2, v3, v4 are the corresponding eigenvectors corresponding to these 4 distinct eigenvalues. The conclusion is that the eigenvectors are linearly independent. Eigenvalues corresponding to distinct eigenvectors corresponding to distinct eigenvalues are linearly independent. We begin with a very simple observation. Suppose V is an eigenvector with eigenvalue lambda. And let us calculate A minus mu I times V. A minus mu I times V. There will be AV minus mu V. But what is AV? AV is lambda V. So is it lambda minus mu times V? This simple observation will be very useful. So now let us get to the proof. Suppose the vectors are linearly dependent. Proof by contradiction. Suppose the vectors are linearly dependent. There exist scalars C1, C2, Ck, not all 0, such that C1, V1 plus C2, V2 plus Ck, Vk is 0. Equation star. Now by renaming the vectors, I may as well assume that Ck is not 0. So I'm going to assume that Ck is not 0, otherwise simply rename the vectors. So Ck is not 0, and I'm going to systematically simplify star. How am I going to simplify star? I'm going to first apply A minus lambda 1 I to star. When I apply the matrix A minus lambda 1 I to star, what happens to the first term? V1 is an eigenvector, remember? So A minus lambda 1 I, V1 will be 0. So the first term will disappear. What will happen when it operates in the second term? A minus lambda 1 I, V2. But by the simple observation, it's going to be lambda 2 minus lambda 1 V2. And there is a C2 already. Similarly, plus Ck, A minus lambda 1 applied to Vk. That's going to be lambda k minus lambda 1 applied to Vk. And there is a Ck already. So this is a new equation I got from star. But this new equation has a pleasant feature that V1 is out. Now I want to make V2 out. How do I make V2 out? Apply A minus lambda 2i. When I apply A minus lambda 2i, V2 will be out. Correct? But what about V3? What will happen when A minus lambda 2 applies to V3? It's going to be A V3 minus lambda 2 V3. So it's going to be lambda 2 so A V3, A minus lambda 2 applied to V3 will be lambda 3 minus lambda 2 of V3. Earlier we had lambda 3 minus lambda 1. And so you get, so we get this new equation. So apply A minus lambda 2i and we get C3 times lambda 3 minus lambda 2 into lambda 3 minus lambda 1 V3 plus dot 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 plus Ck times lambda k minus lambda 1 lambda k minus lambda 2. Because when A minus lambda 2i acts on Vk, you're going to get lambda k minus lambda 2 of Vk. And the Ck is already there, and earlier we had lambda k minus lambda 1 also there. So now in this new equation, V2 is gone. Now I apply A minus lambda 3i and I'll make V3 vanish. So successively everything will vanish, only the last thing will remain. Only the last thing will remain. And we are down with Ck times, at that stage of the game, what is the story? Ck lambda k minus lambda 1, lambda k minus lambda 2, dot dot dot, lambda k minus lambda k minus 1 Vk. Now remember that the eigenvalues were all distinct. Lambda k minus lambda 1 is not 0, lambda k minus lambda 2 is not 0, lambda k minus 1 is not 0. V1, V2, Vk are eigenvectors. Eigenvectors are not 0, but this combination is 0. So the only way this can happen is when Ck is 0, but that's a contradiction because we assumed Ck is non-zero. And that completes this theorem that eigenvectors corresponding to distinct eigenvalues are linearly independent. And I mentioned that k is in general less than or equal to n. What if k is equal to n? Suppose you are able to find a matrix A such that all its n eigenvalues are distinct. If a n by n matrix has n distinct eigenvalues and you take the eigenvectors v1, v2, vn, then you got n linearly independent vectors in Rn. If you have n linearly independent vectors in Rn, what is the dimension of Rn? N. You've got n linearly independent vectors in Rn, they will form a basis. In other words, the eigenvectors of A will form a basis if in this particular theorem K happens to be n, the eigenvectors will form a basis. That's a very important special case. And let us flag that. If suppose you got a real matrix, remember in this particular lecture I'm mostly working with real matrices only. In the next lecture we'll work a complex matrix. A real matrix with complex eigenvalues. It follows that if you have a real matrix with n distinct eigenvalues, real eigenvalues, then you can find n eigenvectors v1, v2, vn, and these are linearly independent and they'll form a basis for Rn. So there is a basis of Rn consisting of eigenvectors of A. This is a very important special situation, and this is called, this has given a name. An n cross n real matrix A is said to be diagonalizable, if there is a basis of Rn consisting of eigenvectors of A. In general, an n cross n real matrix A is said to be diagonalizable if there is a basis of Rn consisting of eigenvectors of A. What we have seen is that if A has n distinct real eigenvalues, implies A is diagonalizable. A real matrix with n distinct real eigenvalues is an example of a diagonalizable matrix. Is the converse true? Is it true that if A is diagonalizable, then it must have n distinct real eigenvalues? No. Take the identity matrix I3. What are the eigenvalues? 1, 1, 1. They are not, they are repeated eigenvalues. But is this identity matrix diagonalizable matrix? It is. By what are its eigenvectors? Every non-zero vector is an eigenvector. E1 cap is an eigenvector. E2 cap is an eigenvector. E3 cap is an eigenvector. So E1 cap, E2 cap, E3 cap is a basis of eigenvectors. So the identity matrix is obviously diagonalizable, and but the eigenvalues are equal. So the converse of this is not true. Remark: it could be a real. It could happen that A is a real matrix, and we have a complex eigenvalue. You've got a real matrix like cos theta minus sin theta cos theta. But the eigenvalue is complex, and you forcibly try to find the eigenvector. You're trying to solve the equation A minus lambda I x equal to 0. You keep performing row operations, and you can do it. Your procedure will go through and you will get an eigenvector, but that eigenvector will be a complex vector. It will not be a real vector. Obviously, it will not be a real vector. It will be a complex vector. We shall see an example in the next lecture. Okay, I think we'll stop it here and we'll continue this capsule.